In this video, or in this section, we're going to be looking at an inverse hypergeometric probability function. So the inverse hypergeometric probability problem is given values that define the hypergeometric probability, that is capital N, capital M, lowercase n, which are in order. The capital N is the population size, capital M is the number of successes in the population, lowercase n is the sample size, and then x then is the number of successes in the sample, and c is going to be a cumulative probability. So we want to find a value for a, which the hypergeometric CDF of and that should say this, just a second. Okay, that's fixed now. So it should say, you have to give it the parameters n, m, n in that order. Population size, number of successes in the population, sample size, and then you give it a lower and upper bound. This is the TI inspire notation, or you get a similar type of thing for the hypergeometric CDF program on the TI-84, and you do n, m, n, 0a, and the c that we're looking for is approximately this value. Okay. Now, this programming will work very similar to the way we programmed in an inverse binomial function. As we will see in Unit 3, a hypergeometric distribution can be approximated by a normal distribution with the same mean and standard deviation. That approximation depends on a few things of how good it is, but we can use that as approximation. Now, recall for a hypergeometric distribution, we have a couple things here. P is capital M over capital N, which is the proportion of successes in the population. Q is 1 minus P, so that's 1 minus M over N. And mean is N times P. Sigma, of course, N times P would then be N times capital M over capital N. So we have that there in terms of our original inputs. And then the standard deviation is the square root of capital N minus little n over capital N minus 1, that extra factor, times NPQ, and then, of course, the square root of the whole thing there. So changing to just our input letters, the P can be replaced by M over N, and the Q can be replaced by 1 minus M over N, or that's the capital N. And so there we get everything in terms of our input letters, N, M, and then the other N. So the function that's going to get us close to what we want for A, at least, is the inverse norm of our cumulative probability C with this mean, N times M over N. So little m times big M over big N, that is the sample size times the number of successes in the population divided by the population size. That's our mean. And standard deviation, put this formula, the square root of all this stuff, as the standard deviation here. So the inverse norm works as cumulative probability, that is probability from there to the left, mean, and standard deviation. And this will give us an x value or a value close to the a that we want. And so we're going to use that this first estimate of an a to give us 3 whole number values for a that are close to this, and we'll produce a table that has a CDF table with the CDFs of all those 3 values. And what we're also going to do is, like we did in the binomial, we're also going to have a column for the proportions as well, because oftentimes we're interested not only just in the x values, but in the proportions. And so in the next 2 videos, we're going to see how to program this in the TI Inspire and then the TI-84.